So, if you happen to be sitting on a commercial flight right now, go ahead and look at the window at the wing.
Yeah, just take a good look at it.
Because pretty much everything we were taught in middle school science about how that massive piece of metal is keeping you in the sky is, well, it's physically impossible.
It really is. It's a universal rite of passage,
Hmm.
you know.
Right.
We all get handed this incredibly tidy, perfectly illustrated explanation in our textbooks that turns out to be pure fiction when you actually test it.
Exactly. And today, we are going on a mission to unlearn that massive childhood lie. We're doing a deep dive into some phenomenal source material from a YouTube channel called Math and Science.
Yeah, the video transcript we're looking at is by an instrument-rated private pilot, and it is just incredibly detailed.
It is, because unless your parents were aerodynamicists or you, like, spend your weekends hanging out in wind tunnels, the actual physics of flight is going to totally blow your mind. I mean, how a plane lifts a 400,000-pound fuselage into the air is not what you think.
Not at all. The real mechanics involve these multi-layered microscopic physics that are just infinitely more brilliant than what those textbook diagrams suggest.
Yeah, the chalkboard drawings.
Right, the chalkboard drawings. Though, to be fair to our middle school teachers, it is easy to see why the incorrect version is taught.
Sure, I mean, you have to simplify it for an 8th grader.
Exactly. It takes a very messy, chaotic reality and makes it digestible.
Well, let's start right there with that incredibly digestible childhood lie, the equal transit myth.
Oh yeah, the classic.
We all remember the picture. The wing is shaped like a teardrop. It's perfectly flat on the bottom with a big sweep curve over the top.
The classic airfoil shape, right?
Yeah,
And the story goes that as the wing moves forward, the air hits the front edge and splits.
right. Some goes over, some goes under.
Exactly. And because the top of the wing has that big curve, the physical path over the top is longer than the flat path underneath.
And here is where the logic just leaps off a cliff for me. The textbook claims that because the top path is longer, the air traveling over the top has to travel faster so that it can recombine with the bottom air at the exact same time at the back of the wing.
Right. And then they drop in Bernoulli's principle to tie a nice little bow on it.
The lower pressure thing.
Yeah, Bernoulli dictates that a faster moving fluid exerts lower pressure. So faster air on top equals lower pressure on top. You have higher pressure on the bottom, which pushes the wing up into that low pressure zone, and boom, you have lift.
But looking at the source material, I just keep thinking, why on earth would the air be obligated to meet up at the end?
It wouldn't.
Right. It's not a synchronized swimming routine. The molecules aren't like holding hands at the finish line.
No, they definitely aren't. What's fascinating here is there is absolutely no law of physics demanding this equal transit theory. It is demonstrably false.
Completely false.
Yeah. When aerodynamicists run wind tunnel tests, where they inject a vertical pulse of smoke ahead of a wing to watch how the flow actually splits, those two streams do not recombine at the same time.
They don't wait for each other at all. The air traveling over the top reaches the trailing edge of the wing roughly 20% faster than the air on the bottom.
Right, it leaves the bottom air completely in the dust.
So while it is absolutely true that the air on top is moving faster, and it's true there's lower pressure on top.
The reason given for it is entirely fabricated. This imaginary synchronized swimming race just doesn't exist.
Which totally shatters the whole paradigm. I mean, if that teardrop shape and the equal transit race aren't the fundamental secrets to flight, what is?
Well, the source points out something so obvious you almost kick yourself for not thinking of it.
Paper airplanes.
Exactly. Paper airplanes, the Wright brothers' original flyer, or even certain modern fighter jets. Those wings are essentially flat.
They don't have that exaggerated teardrop curve on top at all.
No, they don't. Yet they generate lift perfectly well. A flat sheet of plywood can fly if you set it up correctly.
And setting it up correctly really just comes down to the angle of attack.
Right, you don't fly a flat wing perfectly horizontal, parallel to the ground.
You tilt the leading edge up just a few degrees against the oncoming wind.
Yeah, and the source uses an analogy we have all experienced, sticking your hand out the window of a moving car on the highway.
Oh man, I used to do that all the time as a kid. If you hold your hand perfectly flat and level, it just slices through the wind.
Slices right through. But the second you angle your palm up against the wind, the air smacks into your hand and forcefully shoves your arm upward.
You're literally generating lift with a flat wing.
Exactly. And we don't need to overcomplicate the physics here. The relative wind, which is just billions of individual air molecules, is traveling horizontally. It slams into the bottom of your angled hand, or that flat airplane wing, and it bounces off.
Bounces downward.
Right. Because the surface is angled backward, those molecules are physically redirected downward.
You're violently redirecting the air's momentum downward, which means Newton's third law demands the wing gets pushed upward.
Every action has an equal and opposite reaction.
The wing swats the air down, so the air pushes the wing up. Simple, brutal Newtonian physics.
That is the foundation of lift right there. Component 1. If you want to go up, you must push air down.
Okay, but I'm looking out my window at a Boeing wing right now, and it is definitely not a flat plank of wood.
No, it's highly engineered.
Right. If the Newton slap is all it takes to generate lift, why are Boeing and Airbus wasting billions of dollars on complex wing designs? Why not just fly a giant angled rectangle?
2 words. Aerodynamic drag. A flat wing angled into the wind generates lift, yes, but it also creates a catastrophic amount of drag.
Like flying through a brick wall.
Pretty much. The air crashes violently into that blunt, flat leading edge. Instead of flowing smoothly, it separates violently, tumbling over the top of the flat wing in these chaotic, swirling vortices.
Which means your engines would have to burn an unimaginable amount of fuel just to overcome that resistance.
It would be like trying to fly through molasses.
So the teardrop shape isn't the magical creator of lift, it's actually an efficiency mechanism.
Exactly. You put a rounded, thick bullnose on the front of the wing so the air doesn't just smash into it. It's gently parted and guided over the structure.
And just as crucially, you taper the back of the wing into a razor-sharp trailing edge.
Yeah, and this is where the pilot, in our source, brings in a really fascinating detail. He actually used to work on plasma rockets.
Wait, plasma rockets?
Yeah, it's wild, but he draws a brilliant parallel here. He noted that the sharp trailing edge of a wing serves the exact same fluid dynamics purpose as magnetic fields guiding superheated plasma out the back of a rocket engine.
That is an insane comparison. How does an airplane wing mimic a magnetic nozzle?
Well, in a plasma rocket, if the superheated plasma isn't perfectly directed out the back, like if it catches a blunt edge of the thruster, it curls around that edge.
Oh, I see.
It creates a swirling vortex of energy that physically acts like an anchor, dragging the rocket backward. So you use magnetic fields to ensure the fluid detaches cleanly and shoots straight back.
And an airplane wing does the exact same thing for air.
Exactly. If the back of the wing were blunt, the air would curl around it, creating a low-pressure vortex that literally sucks the plane backward. That razor-sharp edge forces the airstreams to detach cleanly without curling.
The wing is essentially a physical magnetic field for atmospheric air. That's incredible. But beyond just reducing drag, this refined shape does something totally counterintuitive with pressure.
Right.
We already established that the pressure really is lower on top of the wing, but our childhood science class get the cause and effect entirely backward.
Radically backward. Think about the airplane flying at 500 miles per hour.
Yeah.
That thick, rounded bullnose at the front of the wing is literally ramming into the atmosphere.
Right.
It violently compresses the air right at the very front of the leading edge, creating a massive pocket of high pressure.
Wait, so if the fat part of the wing is ramming the air at the front, it's acting like a plow.
Yes, exactly like a snowplow.
Which means the curved top surface of the wing is sitting behind that massive compression zone. It's essentially hiding in a shadow.
A pressure shadow. Because the wing is angled upward, and because of that thick front plow, the top surface is physically sheltered from the ramming air.
So what does this all mean? The air over the top isn't speeding up on its own to win a race. It's falling into the ditch the plow just made.
The shape of the wing creates a low-pressure void. And, nature abhors a vacuum. That low-pressure shadow literally sucks the surrounding air into it.
Oh, wow.
The air violently accelerates to try and fill that void on top of the wing.
So the pressure difference causes the speed, not the other way around.
Exactly.
Our textbooks told us the speed caused the low pressure, but it's actually the shape creating a low-pressure shadow that violently accelerates the air.
And this gives us our second massive component of lift. We have the bottom of the wing swatting air down, and we have this low-pressure shadow on top pulling the wing upward into the void.
But this introduces a huge mechanical problem.
How so?
Well, if the air is shooting super fast into this low-pressure ditch over the top of the curved wing, why doesn't it just shoot straight off backward into the sky?
Ah, I see what you mean.
The wing curves downward at the back. Why does the fast-moving air bother to follow that downward curve instead of just launching straight off the top?
That is the million-dollar fluid dynamics question right there. When does the air bend?
Yeah.
The answer relies on something called the Coanda effect. It's the natural tendency of viscous fluids that have internal friction, to stick to curved surfaces as they flow past them.
And the source gives a brilliant, highly relatable analogy for this. Next time you're at your kitchen sinks, just turn the faucet on.
Such a great experiment to try.
Take a spoon and slowly bring the rounded back of the spoon toward the stream of water. The water doesn't hit the spoon and bounce straight off horizontally.
No, it wraps around the curve.
It physically hugs the metal. The stream of water curves around the back of the spoon and flows downward off the bottom edge. When you pull the spoon away, you can visibly see you have bent the path of the water.
That is the Coanda effect in action. Air, even though it feels completely invisible and frictionless to us as we walk around, actually has viscosity.
It has internal friction.
Yes. When that accelerated air rushes over the top of the airplane wing, it hugs the aluminum surface. It faithfully follows the sweeping curve of the wing all the way down to that razor-sharp trailing edge.
And because the wing is angled and the back half of the teardrop curves downward, following that surface means the fast-moving air is ultimately being directed downward as it exits.
Which brings us right back to Newton. The curved top of the wing is using the Coanda effect to grab a massive amount of air and bend its path downward.
And changing the air's momentum downward means the air pushes the wing upward.
The wing is just a colossal air-bending machine.
I am absolutely obsessed with this idea of air grabbing the wing. But, saying it just sticks isn't a satisfying enough answer.
No, we need to know why.
Right. Here's where it gets really interesting. Why does the air stick? How does a smooth sheet of aluminum grab thin air?
To really understand that, we have to zoom way, way in. We have to leave the macroscopic world of aerodynamics and look at the microscopic reality.
Okay, let's zoom in.
There is a fluid dynamics principle called the no-slip boundary condition. When air flows over a solid object, the very bottom layer of air molecules, and we are talking literally one molecule thick, gets permanently stuck to the surface of the wing.
Wait, really? Its velocity is zero.
Zero. Even while the plane is flying at 500 miles an hour, there is a microscopic layer of air frozen to the wing.
Frozen solid.
Frozen solid. And we need a better way to visualize how that creates friction in a fluid. Imagine laying your hand slat on top of a fresh deck of cards on a table.
Okay, I'm picturing it.
Imagine the bottom card is glued to the table. That's our frozen layer of air. When you slide your hand forward, the top card moves easily. But as it moves, it pulls slightly on the card beneath it, which pulls slightly on the card beneath that.
Oh, I see.
The cards slide over each other, but there's a shearing friction, transferring all the way down to that glued bottom card.
That sliding shear is what fluid viscosity actually feels like.
Yes, exactly. That stationary bottom layer of air acts as the anchor. It drags on the layer of air molecules just a fraction of a millimeter above it, slowing them down. That layer drags on the next layer.
It creates a gradient.
A gradient of speed, right, called the boundary layer. This internal friction layer, pulling on layer, is what allows the wing to physically grip the air and bend it around the curve.
But wait, we still haven't answered the most fundamental question.
What's the glue?
Yeah, what is acting as the glue for that bottom card? What is physically locking that very first microscopic layer of air to the aluminum wing?
This is where the deep dive goes completely off the deep end into quantum mechanics.
I definitely did not expect quantum mechanics to show up in a discussion about a Boeing 737.
Most people don't. But the glue holding that bottom layer of air to the wing is a quantum phenomenon called London dispersion forces.
London dispersion forces. Okay, unpack that.
It is the secret engine behind the whole process. We know that molecules like water are highly polar. They have a positive end and a negative end, like little permanent magnets.
That's why water beads up, right? It sticks to itself.
Right. But the air we breathe, mostly nitrogen and oxygen, is completely nonpolar. Those molecules are electrically neutral.
So by all normal logic, they shouldn't be sticky. They should bounce off the aluminum wing like microscopic billiard balls.
They should, if electrons were static dots. But they aren't. The electrons orbiting these oxygen and nitrogen atoms are probabilistic clouds. They are constantly shifting, swirling, and jiggling in space.
The quantum jiggle.
The quantum jiggle. Think of a crowded party in a small room. The people are constantly mingling and moving. Even if the room is evenly distributed most of the time, purely by random chance, there will be fleeting moments where 20 people suddenly clump up on the left side of the room, leaving the right side empty.
Okay, so if we map that back to our oxygen molecule, for a microsecond, The electron cloud randomly shifts to one side.
Precisely. For a fraction of a nanosecond, one side of the oxygen molecule becomes densely packed with electrons, making it slightly negatively charged. The other side is depleted, making it slightly positive.
It becomes a temporary, momentary magnet.
Exactly. And what happens when that temporary magnet is sitting right next to the aluminum atoms making up the surface of the wing?
Well, opposite charges attract. So that momentary negative charge in the air molecule repels the electrons in the neighboring aluminum atom, physically pushing them away.
Yes.
And that creates a momentary positive spot on the wing.
You've got it. For a fleeting nanosecond, there is a weak magnetic-like electrical attraction between the metal of the wing and the oxygen molecule. And this isn't just happening once, it is happening trillions of times a second across every square inch of the entire surface of the wing.
The atoms of the wing are literally pulling down on the atoms of the air, and the air atoms are pulling back up on the wing.
That microscopic electrostatic attraction is the root cause of the no-slip boundary condition.
Wow.
The quantum jiggle glues the bottom layer of air to the metal. That glued layer creates the shearing viscosity. The viscosity creates the Coanda effect, which bends the massive volume of air downward.
And bending the air downward pushes the 400,000-pound plane upward into the sky. That is wild.
It really is.
It is a towering house of cards built on shifting electron clouds. It's beautiful, but it sounds incredibly delicate.
It is delicate.
Which brings us to the terrifying part of the source material. What happens when you push that physics too far and that delicate molecular hug breaks?
That is what pilots call a stall. And our source, being a pilot, gives a very visceral description of what this actually feels like in the cockpit.
Anyone who has watched an aviation movie dreads the word stall.
With good reason. Imagine you're at 3,000 feet. You are flying straight and level, generating plenty of lift. But then, you pull back on the control column. You lift the nose of the plane, increasing your angle of attack.
You're tilting that wing steeper and steeper against the wind.
You are. You're trying to swat more air down to climb faster. But there is a hard physical limit to this fluid dynamic magic trick.
Because of those weak London dispersion forces.
Exactly. That fleeting quantum stickiness is strong enough to gently coax the air to bend around a smooth, shallow curve. But as you make the angle steeper, you are asking the air to make an impossibly sharp turn.
The sheer forces just become too great.
Right. Those weak molecular magnets simply aren't strong enough to hold on to the violently accelerating airflow.
The hug violently breaks.
The airflow entirely detaches from the top of the wing. It stops following the curve downward. Instead, it rips away, instantly turning into chaotic, swirling eddy currents.
Massive vortices tumbling uselessly over the top of the wing.
Just like the drag we talked about with a flat plank. And because the air is no longer being coaxed downward along the back of the wing, you lose that downward velocity vector.
You're no longer pushing air down.
Which means the air abruptly stops pushing the plane up. The lift vanishes instantly. As a pilot, you feel the entire airplane violently shudder as that flow detaches, and then the nose just drops straight toward the ground.
The wing has stalled.
The only way to recover is to shove the nose back down, decrease the angle of attack, and give those molecular forces a chance to reattach and start smoothly pulling the air again.
That is just incredible. So stepping back from the middle school textbook, the actual reality of flight is this massive symphony of physics.
It really is a symphony.
You have the blunt force trauma of the flat bottom of the wing bouncing air downward for a Newtonian reaction.
Component 1.
You have the thick leading edge plowing through the sky to create a low-pressure shadow that aggressively sucks air over the top.
Component 2.
And you have the Coanda effect, driven by the microscopic internal friction of quantum jiggles, grabbing that fast-moving air and throwing it toward the ground. Component 3.
It scales perfectly from the macroscopic brute force of a jet engine all the way down to the microscopic elegance of molecular attraction. Real-world physics rarely fits neatly onto a chalkboard, but the messy reality is so much more profound.
It truly is. It makes the physical world feel entirely interconnected.
And, if we connect this to the bigger picture, and you want to take this new perspective on sticky, bendable air and apply it elsewhere, think about the engineering of race cars.
Oh, like Formula One?
Exactly.
Huh?
Formula One cars are essentially upside-down airplanes.
Wait, really?
Yeah, they use the exact same principles we just discussed. The pressure shadows, the quantum jiggles, the Coanda effect. But instead of using them to lift a fuselage into the clouds, they use them to suck the chassis down onto the pavement at 200 miles an hour.
That makes total sense.
Once you stop seeing air as an empty void and start seeing it as a sticky, heavy fluid, the entire physical world flips upside down.
You'll definitely never look at a spoiler on a car the same way again. So the next time you're staring out that airplane window, looking at the jagged, messy landscape of clouds passing beneath you, you'll know that the forces keeping you up there are just as complex, just as chaotic, and just as beautiful. Thanks for joining us on this deep dive. We'll catch you on the next one.